So as the internet, the routing capacity created a global network. The range of public IP addresses began to diminish pretty quickly. We've mentioned to you before that if we take 2 to the 32nd, if we look at the total number of available public IP addresses with IP version 4, the protocol, the routing protocol that allows everyone to enjoy the global public network we now know as the internet, right? A network of networks, inter-networks, right? The internet, capital I, different than other internets, right? You have small connections, you have branch office connections between local networks. That's a internet lowercase I. Everybody knows what I'm talking about, yes? The difference between the global internet proper and other types of internets, plural?
Yes.
Okay. So everybody needs some way to talk on the public internet in order to be able to pass data to and from that public network. And we noted in a previous class that the number of people in the world has, increased exponentially in recent years. We have 4,294,000,000 that are available. We told you that it was important to have segmented networks for better security, but when you segment the networks, you create barriers between different networks. Devices cannot talk to other devices if they're on a different network, even if the physical layer is the same. Even if they're on the same wire, they can't if they're on a different network. And yet having segmented networks for different purposes, whether you do that on layer 2 with VLANs or you do it with smaller local networks, either way, you have this interconnectivity challenge, and routing is the magic answer. So we run into this brick wall. The public IP address range runs out. And there are 3 major innovations that we now use to resolve the shortage. And that's really important to understand. And each of those are kind of like separate topics. But what I want to do is basically just go to, okay, we ran out about 5 years ago. It's actually more like 10 years ago now. The 3 adaptions, right? The first 2 adaptions are stopgap measures only. That means they're good for a limited period of time. It's like a spare tire on your car. You know, a spare tire. You've all seen the little donut tires on a spare car, right? Everybody knows what I'm talking about. Little donut tire. It's not a real tire. Not a real tire. Okay. The last solution is a permanent and robust solution. And we're going to take quite a bit of time on that last solution in our last module. We're going to swing back and revisit IP version 6. IP version 6 is the best way to address the limitation of public network addresses. And IP version 6 includes 128 bits. You're going to see in a minute just how much that is. It's also more robust in terms of providing for better routing, better link layer services, better security, right? So IPv6 solves a lot of problems. Most of the devices you buy right now have IPv6 capabilities built in. It's just that most internet service providers still don't use it. We're going to investigate the first measure today, right? We're going to be talking about network address translation. Actually, we'll try to talk about both. We'll try to talk about 2. So let's talk about network address translation. Where are we?
Quick thing, Professor Kentop.
Yep.
Will we be doing the packet tracer today?
Yes, we are.
Okay, because I have to go get my dad. So I just wanted to make sure. So I'll wait and then I'll go.
Okay. All right. We just want to cover some basics, some really important basics, and then we'll get to the packet tracer stuff. Okay. So network address translation, right? Public address conservation and better security. On the router that you use at your home and at most businesses and locations, connected network locations, the router includes a service known as NAT, or network address translation. And there's three types of NAT. There's technically the third type is more like a port address translation. We'll talk more about that. But basically what we do is we take a single public address and then we translate that with multiple connections to different ports on the same public address, right? So there are three types of address translations between public and private networks. And there's a YouTube video, right? So it explains NAT and how network address translation occurs. You take a public address on the internet and it's used for your external port, the physical port on the router that connects you to the internet. When traffic comes to and from that, instead of having the public IP address in the header, it's translated into a private internal address. The private internal address is important because private internal addresses by definition are defined as non-routable. You cannot route the IP address traffic on a private network out to the public network. It makes things more difficult for hackers. Put another way, if you're on the public and you get exposed and exploited, and then an adversary gets into your Kool-Aid and takes over your system, they can take your data and they can route it with ease to a distant location on the other side of the planet across the public internet. If you're in a private location, the packets have to be translated into public packets. Now you would say, well, that's done automatically. Depends on the hack. It depends on the scenario. It's a little more difficult. There's a few more challenges when somebody's in a private internal network. If they try to set up a simple routing rule, depending on the security measures in your network, a lot of times those methods are trapped or caught or detected, and then they're blocked. Of the network address translation types, there's what's called a static NAT. What that means is that a single public IP address is translated to a single private IP address. It's a one-to-one translation. So for every public IP address, you're using only one private IP address. That's static NAT. And that's in order to set up things like web servers and email servers. So you set up your public-facing web server and your public-facing email server in a special network called a DMZ, a demilitarized zone, or a screened subnet, meaning it's very tightly filtered by firewalls. And those are exposed to the public network. So they're more vulnerable. And in order for people to find and use email and find and use webmail, the IP addresses cannot and should not change. So static NAT is used for servers that provide public applications, social media and apps, and like we said, streaming media, right? Email servers and web servers. Any question about static? Static means unchanging, and it's a one-to-one. One public address for one private internal address in that screened subnet or DMZ. Questions?
No.
No questions. Okay. All right, hold on.
Quick question, Dr. Kento.
Uh-huh.
Um, there used to be an incident that happened on island where, um, like people who had certain game accounts would get like IP banned.
Uh-huh.
Static IPs help to prevent that, right?
Well, it depends. So the short answer is static IP addresses will actually make it, if you get banned and you're using a dedicated public IP address, let's say you have an internet service provider and you're doing gaming and you purchase a public IP address from your internet service provider. Your internet service provider is going to give you an unchanging public address. So it's static. And then depending on how you use it, the internet service provider, it's easier for the internet service provider to shut you out completely because they're just blocking one address. If it's dynamic NAT, the internal address on your local network changes. And so there's limited public IP addresses, but they're recycled. So with static, it's a one-to-one translation, but typically with dynamic NAT, what happens is that there's a pool of public addresses and not everybody's online at the same time. Let's repeat that. There's a public pool of addresses, public addresses. And since not everyone is on and connected all the time, the pool assignments to a given private internal address rotates. It's recycled and reused, right? So it's more efficient because instead of a one-to-one translation where you only get one address and one address, if you had 10 public addresses, for example, you could service 30 or 40 users with private internal addresses. This same method or strategy is used for the old school telephone systems. They used to have a little thing in your neighborhood called a slick. And the slick was like a little green box, and it was kind of like it was a box full of dedicated phone lines called trunks. And the phone trunks would provide dial tone whenever anybody in a subdivision, you could have 100 homes and have 25 trunks. And so whenever a homeowner picked up their phone off the wall and took it off hook, they needed a dial tone, it would rotate between the 25 trunks to provide a connection out to the central office where the phone company would make the rest of the connection. I'm talking, of course, about circuit switching as opposed to packet switched networks. Circuit switched networks are like the old phone system, okay? And I'm sorry, I should probably circle back and ask, did I answer your question about like internet service providers blocking users?
Yeah, you answered my question.
Yeah, if you have a dedicated address, it's actually easier for the service provider to block you completely and permanently. All right, port address translation is the most efficient, and it uses only one public IP address for an entire organization. So instead of using a pool of public IP addresses, it only uses one. Now, this is typically what you see in homes. You typically have a single IP address. Now I'm going to demonstrate here, just for purposes. I'm going to go out here to, and you've all seen this before, right? Network-tools.com. We have shown you this before in class, yeah?
Yes, you showed it to us.
Okay, or I can go to GRC Shields Up, yeah? This is the public IP address that my internet service provider, Broadband VI, is assigning to my router. Now, please don't all get on DOS prompt and start pinging the crap out of my IP address in a feeble attempt to do some sort of denial of service attack. That won't work. The only thing that'll happen is that you'll likely get blocked by your internet service provider. Back in the day, it was really cute for students to see that. And they're like, oh, let's take down the professor while he's trying to show us something. And they'd all start, like opening up more and more and more windows and just doing massive ping attacks, or running a script to do 100 of them at a time, right? Okay. In any case, the point is that I have a wireless router and I have 12 different devices that are connected, but this is the only IP address that I use. And each of those devices are assigned a private internal network address, but on this network address, they're assigned a different port. Put another way, they have a different port. It's like having a different channel out to the internet. So when you look at GRC Shields Up, and this is a security tool to help you gauge the effectiveness of your firewall. We've all seen this as well, correct?
Yes, we've seen.
Yes.
Okay. What we're going to do here is hit this all service ports option. And yeah, okay, so what you're seeing here on the broadband VI network is commonplace for a lot of broadband VI connections. What this indicates, broadband VI handles its local network a little differently than other service providers. We either have clients on my network or we have clients in the local neighborhood on the broadband connection through radio that are exposed. They have unfiltered, meaning unprotected ports on a firewall that are blinking through. Let's talk about ports though, okay? When you have an IP address, it's a bit like having a street address for a building. And when you have given network ports, it's a bit like having a different door for an office. So this would be like 120, let's see, 80. If I run back this way, port 80 is for the World Wide Web. Right here is the doorway or port that's used by web servers to produce web pages. And these are unprotected web pages. I'm on 443 right here using TLS. I'm using a certificate to encrypt my connection to the web server. And by doing that, I'm actually using a different port. I'm using 443 right here. So you notice it's HTTPS. It's the secure HTTP protocol. Secure sockets layer is what it used to be called. That's been deprecated or retired. If you're on a web server, what you should see is TLS. SSL is like outmoded, outdated, but TLS is the new lingo, the new method, and it uses certificates and it encrypts the connection in much the same manner. It's just not as vulnerable, it's not as exposed. If I want a secure connection to Amazon because I'm buying things and I want my purchases encrypted, I have to use 443. I have to go through this office. But if I'm just getting general information on the old school web, I can connect to a building and go to door for room 80, right? It's like office suite number 80. It's like office doors. So you have so many different office doors in a building, a skyscraper, a multi-story skyscraper, right? And you have all these offices on each floor. And in terms of our network services, there are well-known ports for given services, like port 80. That's a well-known established port for web servers. The first 1,000 ports or so, 0 through 1055, or yeah, give or take a few, these are well-known ports that are assigned. There's a few that are a little higher. 3389 is used for it's used for remote desktop protocols. There are some 1300 that are used for SQL, for database connections. So you can have a database server. And those are beyond the range here, but the point is that there's an established document out on the internet by the international standards organizations, in particular the IETF, the Internet Engineering Task Force, and they've determined which ports are used for which purpose. Now, there are some that are notoriously vulnerable. One example of one that's really, really bad. Did I mention it's bad? It's so bad, you don't ever want to use it. But it's still used often out on the internet to transfer files. It's called FTP. You can set up a web server and turn on the FTP service and then allow people to use it as a repository to download files, much like GitHub, but like really old school GitHub. If you go a little further, just one hop over, one port over, there's a way to encrypt or secure a terminal session, right? So strangely, Telnet is an old way to connect character-based from a screen to a main system, like a mainframe or a supercomputer, a server. And Telnet is also bad. Like FTP, it is unencrypted, and anything you enter for a password travels in the open in plain text over the wire. Don't ever use Telnet. Don't ever use FTP. But if you're on a Mac or you're on other systems, and you can create a remote terminal session using port 22, that's for secure sockets, right? And we'll talk more about sockets, but basically it encrypts the connection so that you're protected. I just wanted to speak to these different ports. And then I want to tell you that there's like 65,000 ports for every IP address. So we could extend this picture all the way down to 65,000 ports. And the thing that I want to impress upon you is that if we use those high level ports, those upper level ports are called ephemeral. Everybody repeat after me. Ephemeral.
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 It's like vapor. Ephemeral means temporary, like a vapor, okay? When a client connects to a server, a client always uses port 80 on the server. But on the client side, they have to use a very high number. And if they use a very high random number, they create a socket that's different than another client across the world that connects with port 80. And someone else is using one of those 65,000 ports, but it's a different one because they're randomly assigned. And the socket to that server still works through port 80, but it's a different ephemeral port. That's how it tells which different clients are connected, right? If you ever get readings on which sockets are in play, you can figure out, okay, I got a live one here, and you can kind of backtrace what's going on with those clients in a manner of speaking. Okay. I wanted to share with you about NAT today, and then I want to stop sharing and I want to talk to you about your packet tracer, okay? And there's one thing I want you to do, all of you to do. We're gonna create a very quick routed network with a router. And then we're going to go into the router, and I want you to show me which interface the route is added to for it to work. Because that's the tricky part. Okay? That's the tricky part. All right. I have to stop my network connection in order to start up my packet tracer because it has some weird little bug in it. And then I'm going to reconnect. So we're going to drop for just a moment, but I want you to stand by. So if it appears that I drop from the session, don't panic and don't run. We're going to do this together in 5 minutes. I want all of you, while you're waiting for me to have my screen up, to get your packet tracer on screen. Okay? All right. So here we go. I'm stopping my network connection. I am now starting my packet tracer. As soon as my packet tracer is online, I'm gonna reconnect. Oh. Everybody there?
Yes.
Okay, so our recording resumed and our packet tracer is in play. Can you still see? All right, can you still see my screen?
No, I don't see your screen. No.
You don't? Okay,
No.
it's not good. How about now?
Yes.
Okay. So we're gonna keep it simple, and I'm gonna move pretty fast. And as I do this, I want you to do this, okay? And we're not gonna worry about the end, the host equipment, the client equipment. We're just gonna worry about the switches and the routers for now, okay?
Okay.
Okay, so I'm gonna take two switches. I'll take a 2960, and we'll call this network 0. And then I'll take another 2960 and we'll call this network 1. Switch 0, switch 1. Network 0, network 1. Okay. Everybody remembers computer architecture and how the first device is always numbered 0 for some strange reason in the binary world, right? It's the first value. What's the first value in the hexadecimal world? 0. Binary and hexadecimal are our digital languages, so to speak, our digital number systems. So we always start with 0, right? Everybody with me so far?
Yes.
Yes.
No, 1 second. Hold on. I'm gonna get it real quick because I had to restart. Okay, coming now.
Okay. Now let's pretend that we have a 192.168.0 network here and a 192.168.1 network here. Okay, everybody with me? .0, .1. That's the network. Everything on there has a 192.168.0.11, 0.12, 0.13. All of the different connected hosts have a .0 something, right? Over here, it's a 1 dot something, 1.12, 1.13, 1.14. And because this is network 0 and this is network 1, and this one's 192.168.0, it can't talk to anything that's over on 192.168.1. Are you with me so far?
Yeah.
Yes.
Okay, now I'm going to take a very simple router. I'm going to take a 2911. So I want you to notice 2960 and 2911. These are like medium sized, easy to work with. They have a few interfaces. They're not huge routers, okay? You can get huge mega routers that are designed to like hook up an entire city, and we're not going to be working with that, right? But we're going to take a 2911 and I'm going to park it here. I'll take a 2911 there and park it there, right? Now notice I have router 0 and router 1, okay? Router 0 and router 1. Now I can insert labels. You have options here to like enter information. You can draw lines or you can put comments. You can do things in here. And you'll notice in the video that I share with you this weekend about your solution, I'm going to walk through all of that. And we're going to have like a label here that says this is the 10.10. something network, and it connects the two routers. Yeah. And then we have another connection here between this router and the 0 network and this router and the 1 network. We want to be able to create routes so that the 0 network and the 1 network can talk to each other. So I'm going to connect my stuff together. I'm going to use the automatic tool and I'm going to go from here to here. Is everybody with me?
Yes.
Remember that routers have this nasty habit of turning off interfaces, right? So everybody see gigabit 0/0? You see how it shows gigabit 0/0 and gigabit 0/0?
Yeah, I'm seeing that. I was about to say I wasn't, but it popped up after.
Yeah, you just got to hold your pointer over it eventually it populates and you see, okay, that's the gigabit 0/0 interface. Okay. On this router and the 0/0 interface on this router. Now I'm going to go from here to here. And I'm going to go from here to here. Now I could have lots of clients and they're all connected to the switch, and lots of clients and they're all connected to the switch. But eventually what you're going to see on this side, if I hold my pointer here, you're going to see this one. Everybody see how this is gigabit 0/0, but this one's gigabit 0/1?
Yes.
Everybody see that? Okay. Okay. Now, this router has a gateway called 192.168.0.1. And this one has a gateway called 192.168.1.1. And anything that's here has to go through that port for a route. I mean, to get out of here, right? So anything on this side that has a packet that wants to get out of the network, you have to hit this port. So the local gateway is 1.1. The local gateway is 0.1, and it's on the 0/1 physical interface. I'm talking about the link layer interface, the physical interface. This Ethernet, if I hold this, well, if I hold it here just right, it's going to show me the little 0/1, right? This router has a 0/0 that connects to this router. Okay. So here's the question I have to ask you. If I'm on the 0 network, which of these 4 interfaces needs to have a route to get to the 1 network?
Repeat that question.
We have 4 interfaces. We have a 0-1 interface, and that's the local gateway on this router. It's the physical port that we would call the gateway for this local network, the 192.168.0 network, right? Same thing here. We have a gigabit 0/1 interface, the second port, the second Ethernet port on that router. So if I look at the router, right? And I want to see on the back, I can actually zoom in, right? I can actually zoom in and I can kind of look at the ports and see, right, which ports are there. So you have a 0/0 port and you have a 0/1 port. Okay. Physically.
I'm having a problem with my connecting the 2 routers together, like it's not drawing a line.
Okay. All right. We can give you a little bit of assistance in just a moment, but I want to repeat the question because this is where most students get hung up. Okay. I have to add a route. A router has to know where to go and which router leads to a given network. Which router leads to the network 1 network, the .1 network? Is it this router or this router?
Right on the right.
The router on the right is the one that leads to the network 1. Does everybody understand that? Which
Yes.
router leads to the network 0? The router on the right or the router on the left?
Left
Right on
router.
the left.
Router on the left. Okay. So if I want something over here to find network 1, which router am I going to need to talk to? Which router is the router for this network? Router on the left or router on the right?
Right. If you want to, you said communicate with network one, right?
Yeah,
Right.
this clients on this network are gonna have to talk to this router, but this router has to know where the router for this network is. Let's repeat that. Clients are gonna talk to this router to try to get to this network. But it's this router that has to have the address of this interface right here. Okay? So it's this interface, the IP address, not the physical designation 0/0, but there's an IP address that's on this port. So remember there were 3 parts to a route. You had the term route add, then you identified the network, and then you indicate, okay, where's the router that does it, right? So this router is going to have a routing rule. It's going to have we're going to add the route to this router, and it's going to say, oh, the .0 network, it's on this port right here. And the clients on this side, when they need to see the first network 1 over here, this router is going to have a rule. It's going to have a route that points to the router for network 1. Well, which router is it that points for network 1? This router. And which gateway is it going to have to hit? Or which port is it going to hit? Is it going to hit this port or this port? Well, this port is the gateway for the internal network. That's not going to work. This is the port that leads to the router that spills down into this network. This is the port that leads inside the router that spills down into this network. The point I'm trying to make is that people get confused and they put the route on the wrong port, okay? So what am I saying? You have to have a route on the same router for that network. But the route has to point to the next hop. It has to point to the next connection or the next router where the other network lies, okay? And you're always working with these ports instead of the local gateway ports, okay? When you walk through the video for your solution, I'm gonna do this step by step and you'll see what I'm talking about. But what I'm saying is that when you assign a network address to 0/0, when you assign a network, an IP address to 0/1, these are like office buildings that need a street number on them, right? It's this public street number you need to have in your route. If you're going from here to the next network over here. So you build the route here, but it references the port there. Let's do the reverse. When you have clients on this network 0 and they want to get to network 1, you have to have a route on this router because the packets are going to hit that router and it's going to go, hey, I need to find network 1. You have to have the route here on the router that belongs to that network. But the last part of the command is going to point to this interface here because this is where you get off for network 1. So you're going to establish a route here, route add. It's going to talk about 192.168.1.0 with the subnet mask, 255.255.255.0. And then it's going to talk about, okay, here's the port on the router you need to get to network 1. It's going to be a 10.10.something.2. And this is .1 and .2, right? So I just wanted to walk through that with you. And I wanted to ask you, okay, when I have this open and I'm doing the configuration, right? Which interface am I working with? Now watch what I just did there. I went to the router, I clicked on it, I went to config, and now what I have to do is select the correct interface to do my commands to set it up. If you click, if you're creating the route on the wrong interface, everything goes south. The thing I want you to remember is if you set it up like we just showed you and connect the two routers first, you're always working with this port. You got to set up an IP address and then do the route. Same thing on this side. You're gonna click on gigabit Ethernet 0/0. You're gonna set up a network address on it, and then you're gonna set up the route. Okay. So you have to have a physical port. You have to have an IP address for layer 3, and then you have to have the route, so it knows where to send stuff that doesn't belong locally. This router will look at every packet that it sees on this port right here, the gateway port, and it'll say, oh, this is a .0. This is a .0 packet. It stays here. Oh, this is a .0 packet. It stays here. Oh, this is a .0 packet. It stays here. Wait a minute. This is a .1 packet. Do I have anything for .1? Network 1. Oh, there's a route. I got to send it to this port right here because this is the router and this is the port on the router that connects me to network 1. Does that make sense? If it doesn't, you're probably going to want to watch me explain that one more time. We'll do it in reverse. I have this router here. It's going to look at the network 1 traffic. Oh, this is a .1 packet. Oh, this is a .1 packet. Oh, this is a .1 packet. Oh, here's a .2, or here's a .0, or here's a .167. It's not a .1, so it goes out. That means it has to go out this port. I have to have a route in here for .0, for the network 0. So I have a route for network 0 on this router, and it says, oh, you got to go to this router because that's where network 0 is. And it lists the IP address for this port on the network 0 router, not the internal address. It's the 0/0 address. Okay. All right, I'm going to stop there and stop recording. And then I'll post this over the weekend along with your solution walkthrough in video. And then we'll use Monday as a workshop to help people do stuff. Okay. Any questions before we
Okay.
break for the weekend?
I have no questions.
No question.
No.